In today's video, we are going to discuss about ventriculo-arterial coupling. So, what is ventriculo-arterial coupling? The concept of ventriculo-arterial coupling tries to see the heart and the arterial system as an integrated elastic system where the elastance of the heart during systole wants to transfer the stroke volume into the arterial system against its elastance, and this interaction leads to creation of flow, that is our cardiac output, and generation of arterial pressures, which is important for the perfusion of the body. Therefore, the relation of the elastance of the heart and the elastance of the artery determines the efficiency with which the heart transfers the energy to the arterial system to maintain a proper functioning of the circulatory system. So, mathematically speaking, ventriculo-arterial coupling is the ratio of the arterial elastance and the elastance of the ventricle at end systole. So, what is elastance? Elastance is the resistance offered by any elastic structure to deformation from its original shape, and if the deformation has happened, it is also a measure of the recoil of the structure back to its original shape. Mathematically speaking, elastance is the ratio of the change in pressure inside an elastic structure by the change in volume. Compliance, on the other hand, is the inverse of elastance, and which is the ratio of change in volume by change in pressure. We often use these two physical parameters in our description of cardiorespiratory system. So, it is important that we understand what is elastance and what is compliance. If we have a pressure volume graph, the slope of any pressure volume curve represents the elastance. So, with this background, let us understand how heart is an elastic structure. So, it is a special elastic structure which can change its elastance depending on the phases of cardiac cycle. So, during diastole, the heart is compliant, or in other words, the elastance is low so that it can fill with blood. During systole, it starts contracting, thereby increasing its elastance to be able to expel the blood onto the arterial system. So, this elastance is therefore a time varying elastance, where the instantaneous elastance at any point of time is calculated by the pressure inside the ventricular chamber at that point divided by the volume at that point over and above the unstressed volume, that is V naught. So, what is an unstressed volume? The volume of blood that an LV can hold in its natural state without any pressure inside the chamber. Therefore, the heart changes its elastance throughout the cardiac cycle within the two limits that are represented by the end systolic pressure volume relation and the end diastolic pressure volume relation. Within this, the heart changes its elastance throughout the cardiac cycle. As we have discussed in our previous class, end systolic pressure volume relation is linear, whereas end diastolic pressure volume relation is exponential. End systolic pressure volume relation is also relatively less affected by the loading conditions on the heart. As we have already discussed, what is an elastance? It is the slope of any pressure volume curve. Therefore, the slope of end systolic pressure volume relation is the elastance of the heart at end systole, or elastance of the ventricle at end systole. In order to understand arterial elastance, we have to conceptualize the left ventricle into as an elastic structure trying to transfer its stroke volume to the arterial system with each systole. Therefore, as the left ventricle empties its stroke volume onto the arterial system, the pressure inside the arterial system rises up to the end systolic pressure. Therefore, the elastance of the arterial system will be the ratio of the end systolic pressure and the stroke volume. It can also be interpreted as the slope of the line joining the end diastolic volume with the end systolic pressure. Now the ratio of this end systolic elastance of the ventricle and the arterial elastance is the ventriculo-arterial coupling, or rather the arterial elastance divided by the end systolic elastance. This ratio is important for efficient functioning of the circulatory system, and it determines the blood pressure that we're going to have, the stroke volume, and the most importantly the myocardial efficiency. If we remember from our previous video on pressure volume loop, myocardial efficiency is the ratio of the stroke work that a myocardium does by the total work that it does. So the idea behind a optimally functioning myocardium is that it will be able to convert majority of its work into stroke work. Now a normal individual has the ventriculo-arterial coupling ratio of around 0.5. At this ratio, the myocardium functions optimally, transferring its energy into the arterial system with each systole. And as we can see from the graph, from the cartoon, the majority of the total work done is converted into stroke work. As in chronic hypertension, or when the arterial afterload starts rising, or in the early phases of heart failure where the end systolic elastance starts going down, this ratio is altered. Somehow the myocardium still takes care of things up to a certain extent with limited cardiac reserve. However, the system is said to be uncoupled when the ratio becomes more than 1. Left ventricular ejection fraction is related to the ventriculo-arterial coupling ratio by this formula. Therefore, if with a ventriculo-arterial coupling ratio of 0.5, the left ventricular ejection fraction is around 67%, which is the normal left ventricular ejection fraction. How do we find out end systolic elastance and arterial elastance? So for arterial elastance, it is pretty straightforward. It is the ratio of the end systolic pressure by stroke volume. However, for end systolic elastance, there are several methods. The gold standard is we do pressure volume loop analysis, and we in sequential multiple beats, and we join the end systolic points of the pressure volume loops. The slope of that point, understandably, is the end systolic elastance. There are single beat methods which have also been proposed. The simplest one is that the EA by EES ratio is the ratio of the end systolic volume by stroke volume, both of which we can calculate from the echocardiography. So this formula assumes that the unstressed volume of the left ventricle is 0, as it is negligible compared to the end systolic volume. However, it may not often be the case, and therefore this formula can bring in some inaccuracies. Another method was given by Chen et al. In their landmark study, where they have defined end systolic elastance as a function of systolic blood pressure, diastolic blood pressure, stroke volume, and the ratio of left ventricular pre-ejection phase divided by the total ejection time. And arterial elastance is again it is assumed to be it is calculated by assuming that the end systolic pressure is roughly around 0.9 of the systolic blood pressure. So the formula is complex. However, there are applications available in for download, where we feed in this data to get the EA by EES ratio. Now, what is the utility of ventriculo-arterial coupling? So far there have been studies which have shown that ventriculo-arterial coupling is often deranged in septic shock patients, and the derangement of ventriculo-arterial coupling have prognostic significance. However, whether targeting ventriculo-arterial coupling as an endpoint or as a target of resuscitation, whether it helps improve the outcome, is something that we still have to explore.